maybe it's kind of nice to start. We tend to build up delays, so let's not build too much of them. So maybe we can just start. Thank you, Shweta, and I'm excited for the second day of the workshop, and it's a great start for it. So I'll give you the floor.
Thanks, Boaz. Thanks for inviting me. It's really great to be here. I'm going to talk about I/O via functional encryption, techniques and challenges from LWE. And as usual, feel free to interrupt me anytime. Let's make it as interactive as possible. All right, so let me start by laying out a quick plan for the talk. So yesterday we already had a series of great talks. First, we saw this great overview by Yael that laid out a series of reductions, showing us how we can reduce I/O to smaller and smaller pieces. And along the way, there was the notion of functional encryption, which implies I/O. And then we saw these three great talks about this new breakthrough by Jane Lin and Sahai, where they identify and leverage a really surprising and beautiful synergy between three very different assumptions, and they succeed in building functional encryption. These assumptions are, of course, LWE, LPN, and SXDH. So my plan for today is just to try and build functional encryption from LWE alone. And well, I'm not going to succeed. So, well, I don't expect to succeed. Don't hold your breath. But what we'll do is we'll identify some technical challenges. And especially in the context of yesterday's talks, what I'd like to do is, just have pairings out there as a comparison point. So let's try to see what challenges we encounter, and sort of taking a step back, we'll try to figure out how is it that using pairings we manage to overcome those challenges, right? All right, and before I begin the talk, I mean, it's a very good question to ask why we should be even attempting to do this. And I have, of course, the standard answers. It's post quantum, three assumptions. One assumption is better than three assumptions. But because Boaz said yesterday that, interesting digressions are welcome, I felt a little bit emboldened, and I'm going to make a very short digression, which I hope you'll find interesting. So, let's look at these paintings by MC Escher, right? And let's look at maybe the one on the left a little bit closely. So here we have these two completely different creatures, a bird and a fish. And we see how they work with each other. They complete the space around each other. They sort of work together in a way that they can manage to tessellate the whole space and create a visual harmony. And Escher, of course, was a genius at this. And on the right side, we have an even more involved example of such a tessellation. Right, so here we have these two very different looking objects or creatures that work with each other. And then here we just have one shape, right? So it's just a simple rectangle. But even here, this rectangle can work just with itself in different ways and also tessellate the space and also create visual harmony. So I'd like to think that for us, it's really not very different, right? So sure, we have different motivations, but it's also nice for us just to step back, spread ourselves out, and figure out what's possible. So, what is it that we can do? From what assumptions can we do it? How do they trade off from each other? How do they talk to each other? Can they help each other? Can we get rid of some of them? So this is kind of the perspective that I'm going to take in today's talk, just trying to examine how things can be if we were to work with LWE alone. All right, so on that note, let's get started. Now, of course, all of you know functional encryption after yesterday's talks, but for the sake of completeness, let me just define it quickly. Functional encryption is encryption with partial decryption keys. You encrypt some message X and get a ciphertext. You generate a key for some circuit F. And when you decrypt, you should learn F of X and nothing else. And security is semantic security in the presence of keys, right? So as long as some of your function keys don't distinguish the output, you should not be able to distinguish two different ciphertexts. And Yael already gave a really nice summary of why FE implies IO and what kind of FE implies IO. So again, I'll just very quickly summarize it. We only need single key functional encryption for a function with long output. Of course, this can be seen equivalently as many function keys with 1-bit output. We need that the ciphertext size should be sublinear in the output length M, and we need to support function class NC0. So this is all we need. I mean, stated like that, it seems, very well within reach, but it's obviously it's not, not so simple. So let's try to see how to build it. And the first and most natural idea that I think many of us have had is, if there's one assumption that seems suitable for this, it should be learning with errors, right? It's learning with errors is amazingly versatile. It gives us this fantastic application of fully homomorphic encryption, which of course, as you know, is the primitive where you can encrypt some input X, compute some circuit F on it, and then end up with an encryption of f of x. So the encryption and function evaluation commute. And LWE gives you very expressive functionality. So you can support arbitrary circuits. It gives you compact ciphertext, which is independent of circuit size. And it's really a perfect solution to this, all or nothing decryption. So if you wanted FHE, well, obviously, barring the circular security issue, LWE is giving you basically everything you wanted. But of course, in this talk and in this workshop, we're interested in partial decryption, not all or nothing decryption. And here, LWE turns out not to so far yield such great news. So we end up with leakage. Okay, and I'm going to talk more about that. So using LWE, we still get this beautiful expressiveness that we know and love about LWE. We can support all polynomial sized circuits while building functional encryption, but we can only do this for restricted security games. So here, unlike the security game that we talked about a couple of slides ago, the game that we can support here is that the adversary only sees a limited number of keys or restricted types of keys or some combination of these. So the adversary does not get to see all the keys that it would like. And moreover, there are attacks against a scheme or, the candidates that we have, there are attacks against them when the adversary violates the security game. So what are the causes of these attacks and what are the possible ways to overcome them? So let's discuss that. The first challenge that we have with LWE based constructions is, what I call leaky LWE keys. So at a very high level, in most, if not all, LWE-based FE constructions, we have the learning with errors embedded in the ciphertext. All right, so that's what the ciphertext looks like, some noisy inner product. And the secret key is an instance of, the dual of the LWE problem, the SIS or short integer solution problem. And what is this problem? So given a fat matrix A over ZQ, let's say, the question here is to find a short integer vector Z such that A times Z is 0 mod Q. And of course, as all of you know, I mean, if this vector need not be short, then this problem is trivial to solve. But if you impose the condition of the vector being small, then this problem becomes very hard. And I'd also like to remark here that if you have many short vectors of this kind in the kernel of A, then these form a trapdoor for A and can be used to solve LWE with matrix A. All right, so now in all these constructions, decryption works when the matrices in the ciphertext and the secret key match up. So you have the LWE instance with some matrix in the ciphertext, and you have the secret key, the SIS instance in the secret key with some matrix. And when these two are the same, that's when we can decrypt, right? So now let's see how to build partial decryption. So let's start with one candidate. I want to encrypt some vector X. I'm going to denote by these yellow boxes, LWE encodings of bit xi under matrix AI. So the exact structure of the encoding is not terribly important for this talk. We'll just say that, these boxes are LWE encodings of these bits. And in a very nice work, Bonnet et al. Showed that these encodings lend themselves to homomorphic evaluation in the following sense. Given encodings of xi, there's an algorithm that lets me compute some circuit on them and end up with an encoding of the circuit applied to the input. So if my circuit is some f, I can compute just like in FHE. I can compute on these encodings and end up with an encoding of f of x. The difference from FHE is that here I'm going to have control over the LWE matrix or the LWE label under which this encoding is constructed. Right, so there's some, A sub f, there's some encoding of f that this LWE matrix is. And correspondingly, there's also a homomorphic key evaluation algorithm, which allows me to just take these matrices, these public matrices and the same circuit F, and also end up with the same matrix that I ended up when I evaluated on the ciphertext, right? So now, using the idea that I told you in the previous slide, that I embed this SIS instance in the key and the LWE instance in the ciphertext, the rest of it just works exactly as I told you before. So the point is that, the matrices in this evaluated ciphertext and in this evaluated key, they match up. And therefore, you can decrypt and recover f of x. So this is, really, really nice. This is a very elegant work and has, been built upon in many, many works later on. The catch here is that X here is not hidden. So what you really get via this scheme is something much weaker than functional encryption. It's something known as attribute-based encryption. We don't need to define it because we don't care about that in this talk. It's very nice on its own, but it's not what we're looking for at the moment. So how can I hide X? That's the question. And there's a very nice work by Gorbunov, Vaikunthanathan, and we that showed that, you can hide X in some settings. So here's a very natural idea, especially given all the talks of yesterday. We're sort of very familiar with this idea by now, that you use fully homomorphic encryption to encrypt this attribute vector xi. Let's call it xi hat. And, let's say that I also give you encodings of the FHE secret key. Now, using the scheme from the previous slide, if I just sort of compose the function with the FHE decryption function, then at least correctness should work out just as before, right? I didn't do anything. I just added one layer of encryption and decryption. I mean, everything else is as in the previous slide. But now my X is hidden. Of course, X is hidden, but sort of the big question is, what about this FHE secret key? I mean, if X was not hidden in the previous slide, then why should the FHE secret key be hidden in this one? And indeed, arguing this sort of takes work. And they managed to do it in a restricted security game where the attacker cannot request any keys such that f of x is 1. So the attacker can only request keys such that f of x is 0. The queries are sort of one-sided. And moreover, there are attacks outside the game, like I said. Okay, so we'll discuss a few of them. One attack that I think is sort of, we we don't often think of it like the attack. We usually think of it is about the leakage or noise, and we'll come to that. But one of the attacks is just about the key structure of the scheme. So here's something that an attacker can do. The attacker can request keys for linearly dependent vectors, and then she can combine these keys to get short vectors and hence a trapdoor for some lattice A star. She can also manipulate the challenge ciphertext to get an LWE sample with some matrix B star. And it turns out that you can make A star and B star match when, the keys are such that f of x is 1. So basically this one-sided security, like I said, there are, multiple problems when you step outside this one-sided security. But one of them is this problematic key structure. So, the fact that these keys are actually sort of vectors that can be combined to get trapdoors of certain lattices, this is really sort of very problematic. And it really crucially exploits the fact, sort of the restriction of one-sidedness. I mean, if you step outside that restriction, then it turns out that you can launch this attack. So a lesson that we learned from this is, that there's essentially a inherent sort of vulnerability when you use this structure of keys. And what's really cool to me is, just looking at this, just looking at this question of leaky keys and how it's such a pain, and then noticing that actually pairings can help you with this problem. Okay, so let's look at how pairings can help you. Now, pairings, unlike LWE, they're not terribly expressive. So, you don't have that much room to move. There are all these problems. One big problem, of course, is the degree, which all of us have hated at some point or the other, this degree too. And the other problem is that you have to end up with a polynomial sized output so that you can do discrete log brute force and recover the output. So that's another problem. So there's very little space that you have to move. But if you can manage to fit your computation somehow within that space, then it turns out that pairings are very, very secure. So whatever you can make happen with pairings will help you a lot with security. So let's see how it helps us in this case. Okay, so now we can build functional encryption for quadratic functions with pairings. In fact, all of yesterday we saw degree 2.5, but for now, let's even just think of degree 2. So, my encryptor is encrypting some vector x. My key generator is encrypting some quadratic polynomial C. And the decryptor computes the quadratic polynomial, on input x. And here we have no restrictions in the security game. So there's no such problem of one-sided security or how many keys or anything like that. So how does this help us here? So what we can do now is we can use, the ideas from before in order to, evaluate on the ciphertext and end up with this encoding of f of x. And let's just look a little bit more closely at the structure of this ciphertext. This is what it looks like. And notice that the encryptor knows sort of some of these values, and the key generator knows the other half of the values in a way that when you take their inner product, you actually get what you want. So you only need like linear functional encryption in order to support this. So the idea is that, I'm going to use a pairing based sort of functional encryption scheme to construct this sort of, the mask. Let's think of CT star as f of x plus a mask. And I can use quadratic functional encryption, in fact, linear functional encryption in terms of functionality, to just compute this mask and remove it out. Okay, and this is what they do in this very nice work by Gay, Jane, Lin, and Sahai. So we can use we can sort of replace these problematic LWE keys with strong pairing keys. And this prevents the attacks that we had on LWE secret keys. So, we can just move to pairings and get rid of this problem, this particular problem. Of course, there are many other problems. All right, so now I don't want to use pairings, right? And in what I showed you in the previous slide, it seems like I only need to compute linear functions. I don't even need to compute quadratic functions. And linear functional encryption, actually, you can build from LWE. But it turns out this does not suffice. It has the same key structure, and there will be other attacks. And there are other approaches from LWE like assumptions or LWE inspired assumptions, but they all suffer from unsimulatable key structures. So, towards the latter half of the talk, we'll discuss some of this. And here's a very nice challenge. So construct LWE based FE with more secure keys. Yeah, sort of just, can we find a way to not have these problematic correlations? And sort of at a very high level, I mean, even if you construct, so in the work that we have so far, even if there are ways to make functionality work, there's a problem in the reduction. And this problem, very interestingly, does not show up in functional encodings. And, we'll talk about this towards the end of the talk. So functional encodings is a really nice sort of weakening of functional encryption. And this particular issue of leaky keys does not come up there. But as far as I know, for functional encryption itself, from LWE, this is a problem. Are there any questions?
Zvika, do you want to ask your question? Yes, I guess the question was answered.
Yeah, I was looking for a tip from someone from the audience, which, yeah.
Sorry?
No, actually, you know what? I don't know what the paper. Someone sent me the paper. Okay. No, I just didn't know what was one of the references that you were mentioning, but I do now. So thank you.
Okay, sure. Does this make sense?
Makes sense to me. Although actually, here's a question for you, Shweta. Do you have any proposals or any thoughts you've thought about, like what is a intermediate notion of more secure key that's not all the way to functional encryption, but is still some non-trivial progress?
So I mean, that's a really interesting question. I don't exactly know how to think about an intermediate key here. So as I was mentioning, the real problem here is that even if you can get the functionality to work, which we do, right? The problem in the proof is that these keys, so at a high level, these keys are, these SIS vectors, right? And they need to be, they need to be short pre-images to correlated vectors. This is the problem. So the images in the SIS problem, so you have, AZ equals U, right? This is your SIS or ISIS problem. And the U's in these equations are going to have to be correlated. So in your reduction, what you need to do, you don't have any trapdoor for the A. So typically in basically every system, you sample the SIS instance and you set the image accordingly. But now the problem is that, you cannot really do that because you can't sample these things and get these you don't know how to get the correlated images. So this is the problem that comes up in the reduction. And I don't really know what's a intermediate notion that one could be looking at. In fact, I was really, really happy to see this idea of split FHE and functional encodings / functional encodings, because you don't run into this issue here, and I hope to talk about this at the end of the talk. But yeah, it would be, I mean, I've structured this talk in this slightly high level kind of a way, hoping to sort of, you know, take a look at the technical barriers. But I'd really love it if, you know, someone could let me know when something is not clear.
So I actually have a quick question. It seems like there should be some advantage we get from the fact that for I/O, we don't actually need to evaluate an arbitrary NC0 circuit. We just need to evaluate the decryption circuit. And that seems like it should play into the fact that we can get functional encryption for reduced queries and reduced types of queries, because we don't need to actually allow the adversary to get arbitrary functional encryption keys. The adversary only needs to be able to get the functional encryption keys corresponding to the decryption circuit that they want to evaluate for I/O.
But we have to be careful here, because when we say that it's only the decryption circuit that the adversary needs to evaluate, that's true. But the decryption circuit should only be applied to an encryption of f of x.
Okay.
You know, I could, for instance, if I had a key that would work, give me decryption for any encoding of my choice, then I could even go back and decrypt my original encodings, right? And that wouldn't work out. So it's not, yeah, that's not really helping us too much. I mean, of course, the structure of the decryption circuit and flooding, all of that stuff helps, but yeah, the function does play a role. All right, so you know, that was the first challenge. So how to design FE from LWE where you don't have these problematic correlations between the keys. The second challenge, of course, is, you know, how to compute smudging noise. So I'll describe, you know, this problem in more detail. But since we've seen a day of talks yesterday, we know that when we do this FHE decryption, however we do it, there's inner product plus rounding. Now we don't, you know, we often cannot support rounding. So as we saw yesterday, we can instead sort of flood the decryption with some noise, and this should drown out the leakage in the original noise, right? So this smudging noise needs to be computed, and a great question is how to do it. In fact, this turns out to be one of the thorniest questions. And all the works that have done this have used some variant of what I call degree flattening, right? So what's degree flattening? Well, I'm given an LWE encoding of some input X, and I want to compute some deep circuit, you know, F on X to obtain an encoding of F of X. So degree flattening is the idea that, you know, we represent a deep computation F as some equivalent function, such that this new function has to only do a high degree computation on the public encodings and only a shallow computation on the private stuff. Right, so like we saw in the previous slide, there was this FHE secret key hanging around that needed to be kept private, but the FHE encryptions could be kept public. So this is an example of degree flattening, and we'll see more examples, right? So if I want to stick to, you know, LWE based solutions alone, then sort of one idea that I might try to do is let me flatten the degree all the way down to linear functional encryption, because I know how to do linear functional encryption from LWE. I don't know quadratic, but I do know linear. So is it possible for me to use this idea to bring the computation all the way down to linear? And, you know, just as a very quick recap, this is linear functional encryption. So you have an encryption of X, you have a key for Y, and decryption outputs the inner product. And again, there are no restrictions in the security game. But, you know, the functionality of linear FE is so weak that there's no security for against an adversary who makes n independent key requests, right? Because such an adversary gets n linearly independent equations in the input vector X and can recover the whole X just bilinear algebra. So I'm wanting to point out that the security, there's no restriction in the security game, but this functionality itself is very weak. And moreover, in the construction, what happens is that because the security game is weak, it turns out that it's actually okay to leak a little bit of the MSK with each key request. And in the construction, once you have more than n key requests, the entire master secret key is leaked. And within the security game of this scheme, this is actually all right. So now let's see how we might try to do this degree flattening, and go down to linear functional encryption. So I'm going to start with this very nice scheme by Brzezinski and Vaikunthanathan, where I think this idea was born, at least for me. And here's how I want to encrypt, right? So this is a secret key FHE scheme, and let's just look at quadratic polynomials. So in order to encrypt some messages x1 and x2, I'm just going to sample u1 and u2 randomly and generate LWE samples, which I use then to mask these messages. And now I want to, let's say I want to compute an encoding of x1 times x2. So the very nice idea that they had is, let's look at what we want to decrypt. So rather than staring at the encryptions and how to manipulate them, let's rather stare at what we'd like to decrypt and see if we can somehow manage to decrypt that. And this is what they observed, right? So the product x1, x2 can be written as approximately equal to this, term on the right. And they suggest that you can just set this product ciphertext as this tuple. So C1, C2, C1, U2 plus C2, U1 and U1, U2. And if you take the inner product of this tuple with, this other tuple or other vector which depends on the secret key, then of course you get back this equation, and that means that you recover x1, x2 up to noise, which you manage to round away. So can we use this idea in the context of functional encryption? And it turns out that we can, right? So let's look again at this FHE decryption equation. Actually, first of all, let's notice here that the way that we wrote the decryption equation here is not at all useful for functional encryption, because this 1s and s squared, this is not encoding any function, right? So it's all or nothing. If you have this, you can decrypt everything. If you don't have it, you decrypt nothing. So now if I want to do restricted decryption, then let me try to do it a little bit differently. So I'm going to write my FHE decryption equation as before, but this time I'm going to group the terms differently, right? And what we can observe here is that this decryption equation now can be written as C1, C2, which is like a function computed on public data. So C1 and C2 are already LWE encodings, they don't need to be hidden, right? And this plus an inner product of two vectors such that one can be known to the encryptor and one can be known to the key generator, and just taking their their sort of inner product suffices for decryption, right? So the encryptor now can actually just provide these LWE encodings C1 to Cn, as well as a linear functional encryption of this other vector, and a linear functional encryption key for the corresponding vector, so that computing C1, C2 herself, the decryptor can recover this equation. So the key insight here is that the quadratic terms are, Ci, Cj, which are public and can be computed by the decryptor herself. And you can make do with only 2n encodings instead of n squared. So you got this compression that you wanted, right? So you got that the deep computation is on the public encodings, and the shallow computation or the key dependent computation, this is only linear. And moreover, this can be generalized, all the way to NC1, which sounds great. So you do get NC1 even with sublinear ciphertext. But the problem is that, if you do this, then it's not secure. And why is that? Because here we allowed the decryptor to learn this linear equation in secret terms. And this is an exact linear equation. So this is too much leakage. So the adversary is now just getting exact linear equations, and this is problematic. But what now again, let's look at what can happen if you have pairings. Now, if I don't squash the degree all the way to linear, but I squash it only up to quadratic, then what happens? Then the adversary is seeing quadratic equations in secrets. And this, this is now like the multivariate quadratic assumption for some distribution. So this we can actually hope is secure. So if I have quadratic functional encryption, I'll just squash the degree down to quadratic. The adversary will see quadratic equations, which, so you manage to squash the degree, you're still computing high degree terms, but because the secrets are hidden within quadratic equations, the adversary hopefully cannot learn anything from that. Right, so the degree reduction to linear with LWE is too much, and we're forced to do this, or we're forced to try this, I should say, because we don't have quadratic FE from LWE. So that's a problem. So what might we do? Well, so previously in the previous slide, I said that multivariate quadratic equations may hide secrets. But noisy linear equations also hide secrets. So as we already know from yesterday, if we find a way to generate noise and sort of hide this, add this noise to the exact linear equation that we saw, then this can be secure. This can be provably secure. Okay, so that's going to be the rest of my talk. So, how could I hopefully construct FE for linear functions plus noise? It's a good time to take questions if there are any.
Any questions? And you have about 15 minutes, is that okay?
Sure. I'll probably have to skip some stuff, but
no, you could go a little bit over time. So let's say between 15 and 20.
Okay. Yeah. All right. So in what time I have left, I'm just going to try to, sketch a few additional ideas. So we already defined linear functional encryption. Now let's look at a generalization called noisy linear functional encryption, where the encryptor has X, the key generator has Y, and the decryptor should get, the inner product of X and Y plus some noise. And a special case of this is via the degree 2.5 FE that we saw yesterday, which is also basically, finding a way to compute a PRG output as noise. So, of course, the big question is, where does this noise come from and what security properties does it need to satisfy? So it turns out the noise need not satisfy too much. It needs to satisfy some mild statistical properties. But a nice observation we can make here is that, the exact value of the noise term is not important. So maybe computing a noise term is somehow easier. Maybe somehow we can do some kind of approximate computation. And we find a way to do that, but, not from a great assumption. So the key observation I like to show this slide is that, it's sort of this thing that everybody's heard. Like if you can't have what you want, you should learn to want what you can have, right? So in our context, if you can't compute what you can use, then you should learn to use what you can compute. I mean, from LWE, we don't know how to compute a PRG. So can we do something? Maybe can we strengthen LWE in some way so that it enables some kind of approximate computation? And maybe that will be good enough for our purposes, right? And this was the hope. So instead of, computing X inner product Y plus G of seed, where G is a PRG and seed is the seed, it's okay if I compute X inner product Y plus G prime seed prime for some, variant of G and some variant of seed. And the observation was that only the inner product needs to be exactly correct. The G of seed is in fact allowed some corruption. So far, we assume that the polynomial is a PRG and insist on computing it exactly. But maybe it's also possible to compute whatever LWE or something like LWE allows me to compute and then check if it can satisfy PRG-like properties. So let's try to build it. From LWE alone, we don't know how to, but we have a way to extend this LWE-based linear functional encryption scheme to this using new hardness conjectures. Okay, so given that I don't have a lot of time left, what I'm going to do is sort of just try to sketch some of the main ideas here. Yeah, so I just want to give you a taste for what the assumptions look like. As I already mentioned, the hope is that, approximate computation should somehow be easier. And what we're going to do roughly is we're going to use these LWE labels and these LWE errors. We're going to pick them in a much more structured way and, hope that nothing bad happens. So the LWE labels look like this. So, these are n-true samples, except that we reuse some of the denominators. So these are, these terms look familiar from multilinear maps as well. These in general can be conjectured to be pseudo-random. This, I think, is actually not the problematic assumption. The sort of more problematic assumption is that what we're going to do is we're going to compute LWE samples with structured noise. And this noise is going to be structured in the following way. It will live in some fixed secret ideals that, cancel out nicely with these public keys. So this is what my error will look like, what's in the pink box. Okay, so let's say that G1 and G2 are secret. These are, note here, they're in the denominator of these, of the public key terms. So the main thing that we did is that we set it up so that the cross terms between the errors and the LWE labels are small. And what this allows you to do at a very high level is, it allows you to give these LWE sampled with structured noise, so that when you multiply these encodings, you end up with like a nice LWE sample that fits back with the rest of your scheme. Okay, so let's say that this is what our encodings look like. The encodings look exactly like regular LWE encodings, except that they have this structure, right? And now when I multiply them, then I get something that looks quite nice. I mean, it looks like, an LWE label times a secret plus noise, which is sort of what I wanted. And this fits back in with the linear FE scheme. So I can sort of generate encodings of noise in this way and fit it back with the linear functional encryption scheme to sort of get a functional encryption scheme that computes a PRG. That's kind of the main idea. So notice that, what we're really trying to do here is that if you want to have, let's say, M encodings of noise, right? You want M encodings of noise because each encoding should smudge, one output bit of the PRG. So when you want M encodings of noise, what we're trying to do here is we're trying to compress, just like in pairings, right? So we're trying to sort of give somehow square root M samples such that they can multiply with each other and expand into M samples in a way that's okay. And now this noise that we get, I mean, this looks ugly, but it can be set up so that it has the structure of a PRG, and we can conjecture that it suffices to smudge the original noise it was trying to. So yeah, I like this theorem. It's easy to make noise. Of course, there's another theorem which says it's not easy to make very good noise, but at least noise, I mean, there are multiple ways in which one can hope to generate noise. So in terms of security, the proof is from a clumsy assumption in an overly weak security game. And in the full-fledged game, we only hope for security. It's based on the inability to find attacks. There are a few hurdles in the proof. So like I was alluding to earlier, the problem is that, we're trying to get this compression that, we've been talking about all of yesterday. And this compressed public key, it's correlated, right? So or rather I should say that when I expand it back, I get something that's correlated. And I don't know how to simulate secret keys for these correlated images. This is one of the problems. So in general, we get an interactive assumption, but it can be made non-interactive if the adversary only gets one ciphertext. So, we don't have to address this hurdle if the adversary only gets one ciphertext. And this brings me to the connection with functional encodings. So functional encodings are similar to functional encryption with only a single ciphertext, because the counterpart of key generation, it can have the message X as an input. And in fact, okay, so yeah, this is all I'm going to say. So in this setting, the assumption that, we had from our previous work can be made non-interactive. As it is, it does not achieve the compression that you require for functional encodings, but it can be modified to do so. So I don't have time to talk about this. Maybe it's a whole different talk, but the construction that we have here that's trying to build functional encryption can really be seen as a dual of the construction from the WW20, even in the sense that, we use dual regger and they use primal regger. And there's a very nice connection that sort of emerges. So, okay, and in particular, like for the weaker setting where we only need to have security for a single ciphertext, we can also make the assumption non-interactive. But the leakage or correlation in the noise, there's sort of another hurdle that has to be crossed. And this hurdle actually appears in both works. So even if we sort of look at the weaker game required by functional encodings, and even if we manage to make the assumption non-interactive, we don't manage to overcome this hurdle of the correlation in the noise. And this is sort of there in both the works. So we cannot improve the WW20 assumption, even for functional encodings. In fact, our assumption is going to be worse because it will also have this structured and true stuff, which they don't need. And it will have the leakage, which they also have. But on the other hand, it gives functional encryption, which is stronger. So, I mean, the big question that, okay, sorry. So I wanted to also quickly summarize. So here are, 3 nuggets for thought. One is how to strengthen LWE keys. Is it possible at all to generate smudging noise using only linear FE? I mean, my guess would be no, but maybe it's possible somehow. And a third question is, can we perform approximate computation more easily? So the fact that we only need to generate noise, does this help us somehow? So open problems, right? So obviously the big question here is to overcome these hurdles and get a construction from LWE. But in the absence of that, can we maybe replace pairings with some weaker structure that can be built from LWE? Can we maybe have new, simpler, plausible assumptions from lattices? So this is a question I really care about, and I keep asking it in every talk. I mean, with lattices, we have LWE, which is perfection, and then we have like multilinear map-based assumptions, which are fairly complex. Surely there's stuff in the middle that exists, right? I mean, can't we come up, and we have some nice examples, like there's this entropic LWE assumption and such. But I feel like we could hope to do a more systematic study of what are the sources of hardness in lattices that that are stronger than learning with errors, but somehow still very clean and plausible. uh, yeah, this idea that noise computation need not be exact, is this something that we can use in a better way? And lastly, I think that IO, of course, is amazing, but it has this problem of the sub-exponential loss, which we discussed yesterday at length. Functional encryption as a primitive does not have this loss. So I think that it would be also very nice, to have, I don't know, functional encryption from circular LWE, like, just how we have functional encodings. Can we do functional encryption with some similar assumption? And can we base applications on this rather than on IO, so that we can avoid that loss? That's all I had. Thank you.
Thank you, Shweta. Are there any questions?
Shweta, I just wanted to say the noisy linear FE notion that you have, it seems very similar to this oblivious LW sampling that, because I'll talk about it then. In some sense, I don't know about the exact definitions, but somehow morally, it seems to let you.
Yeah, I completely agree with you. Sorry, I should let you finish your sentence.
Yeah, I was just gonna say it seems to let you obliviously create LW samples, right? Without knowing the secrets you somehow.
Yeah, exactly. And so, what I was trying to do was exactly what you are also trying to do, which is compute these LWE samples obliviously. Since in the case of functional encryption, it needs to work for a lot of ciphertext. You have to use SIS instead of the LWE secret. So instead of primal regev, you have to use dual regev, because it has to work for many ciphertexts. And what we were trying to do was just find a way to compress these encodings of noise, right? And that's exactly what oblivious LWE sampling also gives you. So the two schemes, in hindsight, they're very nicely connected, I think. And as I said, I mean, in fact, in your paper, you asked this question, like, can we improve the assumptions in prior work now that we have functional encodings? And I thought about our assumptions, whether we can improve them. And like I said, so the interactiveness can indeed go away. But the entro stuff kind of almost becomes pointless, because you don't need that anymore. And the leakage, that does not go away.
Yeah, it seems like doing oblivious LW sampling through this framework of functional FE sort of imposes additional constraints that make it harder in your work. And
I mean, it's a much stronger primitive, right? Because the security game is so much stronger. You have to support sort of unbounded number of ciphertexts. So that's why this notion of split FHE or functional encoding, it's really, it's very, very nice in the context of IO, because it really does weaken functional encryption quite substantially. So yeah, I mean, I used to never think that purely from LWE IO will be possible, but via functional encodings, maybe it's possible. So since Zvika was uncharacteristically optimistic, let me be uncharacteristically pessimistic. So functional encryption from LWE alone, I somehow feel a bit pessimistic, but I would love to be proved wrong. Yeah.
Great. So let's take just a 2-minute break, and then Julia, you can already start sharing your screen. I posted on the chat, by the way, there will be a ramp session today, and people are very welcome to give some brief talks. And so please put your proposals in the Google Doc, and Yael will be hosting that ramp session. So that will be at, let's look at the schedule again, at 1:20 Pacific. Okay, and let's start in